So after considering cellular respiration, taking glucose through the stages of cellular respiration to make ATP, what we want to consider is alternative ways to make ATP, specifically fermentation and then feeding other biomacromolecules into these metabolic pathways to make ATP. So again, we know in cellular respiration we've got our three major stages: glycolysis, the citric acid cycle, and then oxidative phosphorylation, right? The thing that you need to remember is the idea that you can get some ATP, though much less, from the first two stages. So again, we know that oxidative phosphorylation is by far the greatest yield, but we still get some ATP from glycolysis, and sometimes some is better than nothing. Okay? Sometimes some is infinitely better than nothing when nothing results in death, and at least a little bit of ATP lets an organism continue to live, albeit without oxygen. So again, when we say cellular respiration, it's almost implied that you're talking about aerobic respiration. We did talk about anaerobic respiration, but most people will assume you're talking about aerobic respiration with oxygen when you say cellular respiration. So we're taking glucose, generating NADH ultimately to put into the electron transport chain to generate a proton motive force to make ATP, and that depends on oxygen as our terminal electron acceptor for an electron transport chain, because that electron transport chain is what's going to be pumping protons across the membrane to develop a gradient. All right? So quick review there. Now, fermentation is an alternative pathway when you don't have oxygen. Now, there's lots of different kinds of fermentation out there. We're going to look at two types: alcohol fermentation, that most people are familiar with from yeast. This is how we make wine and beer, alcoholic beverages. And then lactic acid fermentation, which we see in our muscles when they're oxygen stressed, yet still have a demand for ATP. So let's look at alcohol fermentation. And in this biochemical pathway, what we're doing is taking pyruvate and we're converting it to ethanol in two steps, releasing CO2. So what we're going to basically do is gain the ATP and the NADH that we get from glycolysis, but instead of feeding the pyruvate into the mitochondria, we don't, because there are indicators that that would be fruitless. If there's no oxygen, that means electron transport isn't working. There's no reason to build up more NADH because we can't use it. So what we're going to do instead is direct that pyruvate not into the mitochondria, but down a different biochemical pathway, where we're going to convert it into acetaldehyde and then ultimately ethanol. Now, the key to this and the key to fermentation is the idea that in that process of producing ethanol, we're going to need reducing power. And we're going to use the NADHs that we're generating glycolysis up to make NAD rather. So the ATP is going to be harvested to try to keep moving the cell forward and alive. And the NADH has to be used up, because if we don't convert NADH to NAD, then glycolysis itself would stop. All right, so I want you to think about that. Right? What do I mean? So let's look at glycolysis. So as we go in, we make our input, our 2 ATPs, in our investment stage, and then we reap the rewards of that investment with 4 ATPs, so a net gain of 2, but we're also producing this NADH. Now, if we don't use the NADH, which we won't do in the absence of oxygen, ultimately what we're going to do is deplete all the NAD. If there's no NAD, we're never going to get past glyceraldehyde 3-phosphate. We're never going to make those 2 more rounds of ATP production to make enough net gain of ATP. Does that make sense? So if we lose our pool of NAD, we can't make any ATP. We can't move forward in glycolysis. So it's essential then that we use up that NADH to NAD in the process of making ethanol. Ethanol then is a waste product, right? And ultimately it's poison. Right? If that builds up to high enough concentrations in the media, it will kill the cells. All right? So this is the idea of fermentation. Now, lactic acid fermentation is a slightly different version, the difference being that now instead of producing ethanol, we produce lactic acid or lactate. Right? But again, the point here is that in the process of going from pyruvate, the end product of glycolysis, to lactate, we're going to use up NADH to replenish the supply of NAD so glycolysis can continue. And if glycolysis can continue, then we are still making ATP, again, albeit a much, much smaller amount. So these are two reactions that are not that complicated, but you should understand them and have them in your head. Fermentation, alcohol fermentation, lactic acid fermentation. Right, so again, bottom line fermentation, our net gain is 2 ATP per molecule of glucose. Aerobic respiration, net gain 38 ATP. So it makes you think why there are so many organisms that are very successful on this planet that do aerobic respiration, right? So it's a very, very efficient way to make ATP, much, much more productive than just fermentation, where we have the absence of oxygen, right? So again, this is going to happen now in the cytoplasm. So when we have that pyruvate molecule, no O2 is present. We're going to shuttle our things towards fermentation. O2 is present. We're going to go aerobic cellular respiration. These are facultative anaerobes. These are organisms that can survive either on fermentation or on aerobic respiration. So we are not facultative anaerobes, though we do short-term lactic acid fermentation. So obligate anaerobes are organisms that only do biochemistry in the absence of oxygen. So they're going to get their ATP from fermentation or anaerobic respiration, both of which are not as efficient as aerobic respiration. Why? Because again, oxygen is such a strongly electronegative element, it has the biggest differential between the free energy of those electrons in their starting organic molecule and when they make water, basically, at the end of the electron transport chain. Now, facultative anaerobes can switch their metabolism between with or without oxygen, right? So yeast can do this, and many species of bacteria can do this. So in that respect, we are not as advanced in our options. Now, glycolysis is, like as I mentioned before, is a very, very ancient pathway. It is in nearly all organisms. So it probably developed in very, very early prokaryotes before there was oxygen in the atmosphere. So we probably fed this thing into fermentation or something, anaerobic respiration at that time. But what we're also going to see is that because it's so old, it is at the kind of crossroads for many, many different metabolic pathways, right? And there are charts out there, if you Google it, you can see these charts that just look like, huge roadmaps, but you'll see how much they converge on these respiration pathways. So that brings us then to our versatility of catabolism, right? We can't just be dependent on sugars for energy, right? We can break down sugars, as we've noticed, to make ATP, but we can also feed fats and proteins into these pathways. And that's why the intermediates of these pathways are so important to know, because it's at those intermediates, if I can derive those intermediates from some other pathway with the starting material being fat or protein, I can feed it right into here and pick up at that point and move towards oxidative phosphorylation. Right? So let's take a look at that. So again, catabolic pathways funnel electrons from many kinds of organic molecules into cellular respiration. So a wide range of carbohydrates. It doesn't have to be just glucose. Proteins and fats can all feed into this system to make energy. So that then we can address the question, why are fats so high in energy, right? Because we talk about, if you pick up a food item, you see you get 4 kilocalories per gram of protein and carbohydrate, yet you get 9 kilocalories per gram of fat. More than twice the energy, the calorie output for an equal weight of fat. Why? Well, there's a whole lot of carbon-carbon bonds in fat. And if we go back to our structure, let's look at that fatty acid. Let's look at that fat molecule, that triacylglycerol. It's a whole lot of carbon-carbon bonds. Now, what we're going to do is a process called beta oxidation. Now, beta oxidation, what it's going to do is start to cleave off 2 carbons at a time. And what we're going to do is take those 2 carbon units and build acetyl-CoA. Acetyl-CoA. A car in Kansas stops slowly for more oil. That is the first step in the TCA cycle. So if I can take fat and start producing acetyl-CoA, I can start turning the citric acid cycle, and that's where I'm going to produce the majority of my NADH, my FADH, and a little bit of ATP. That all then can be fed into the electron transport chain. So if I'm looking at this, the longer the fatty acid chain, if I'm looking at this, every 2 of those carbons is going to turn the wheel of the TCA cycle once. I'm turning that wheel dozens of times per one fat molecule. Where when I have a glucose molecule as my starting point, I turn it only twice. So all of a sudden now it becomes very obvious how you can feed this into our basic metabolic pathway and get a tremendous amount of energy from that fat molecule. All right? So why it's also important to think about these intermediates is that we can break things down into an intermediate and then shuttle them off to other pathways. It doesn't have to always be used for energy generation. We can use this to build other biomacromolecules in anabolic pathways, right? So controlling this is very complicated, but we can look at a couple of very important points of control. And if you think about it, the end product really is ATP. So if ATP concentration drops, you really need more ATP, and usually pretty quickly. So respiration is going to always speed up when we're low on ATP. If I have plenty of ATP in reserve, I'm going to slow it down because I don't want to waste my energy making ATP that I don't need. So if we look at some of those control points, phosphofructokinase, the conversion of fructose 6-phosphate to fructose 1,6-bisphosphate, is a big control point. If I have AMP in abundance in the cell, that's going to stimulate phosphofructokinase. I'm going to be pushing things faster through glycolysis and hopefully then into the rest of this metabolic pathway to make more ATP. At the same time, if I have plenty of buildup of the intermediates, citrate, for example, a car in Kansas, citrate builds up in the citric acid cycle, that's going to say, whoa, there's plenty of citrate around here. We're running strong in the TCA. Let's slow down the production of more pyruvate and more raw material being fed into the TCA cycle. So that's going to act as an inhibitor of phosphofructokinase. ATP itself then can also inhibit phosphofructokinase. So again, if we look at the glycolysis as a pathway, that step 3 going from fructose 6-phosphate to fructose 1,6-bisphosphate, it's a very important enzyme. That's a big knob, a regulator, turn it up or down for control of this whole system.